So we're going to look at calculating higher order derivatives or derivatives of derivatives today. We're going to start out with kind of an application of where this is done. So in physics, if you're working from a position function where something is, and I take the derivative, I get the velocity function, which tells me how the position is changing, right? So kind of like the slope of the position. But sometimes I also want to know how the derivative or the velocity is changing, and we call that acceleration, right? So we sometimes think of acceleration being speed changing. I'm not going to get into the difference between speed and velocity, but that's another way we can think about it. So this is just showing why we might care about the second derivative. Here we have notation. So basically, we just keep adding primes on. For the second derivative, the third derivative, if I'm beyond the third derivative, I use little numbers and parentheses to represent which derivative I'm on. Notation is a little weird with dy dx. When I talk about the second derivative, I actually put the 2 in between the d and the y, but I put it after the x on the bottom. Over here, there's a little notation just explaining why that is. If we write dy dx, we're saying changes in y over changes in x. When I'm taking the derivative of the derivative with respect to x, we end up with 2 d's here. So we write d squared y, and then we have 2 dx's, so we write dx squared on the bottom. So not really important to know, remember that, just know that's how you write it with the dy dx notation. So we're going to take a second derivative, and they are pretty easy because it's just the derivative of the derivative, so there's no new rules. So if I want to get to the second derivative, I just take the first derivative, which is 6x squared. This would become plus sine x plus 1 over x minus e to the x. And then the second derivative, or the rate of change of the derivative, so I'm going to go through the line again. So this is going to give me a 12x plus cosine x. Derivative of sine is cosine. This is x to the negative 1. So I'm going to get minus x to the negative 2. And then we know e to the x stays the same. So that is the second derivative. Here's a little applied problem. We'll use the second derivative a lot in the next unit. In certain applied problems, but we're going to do one now just so you get an idea of how it can be used. So we have a situation about a ball being dropped from a tall building, and the position function is given by this, where we are using feet, which bothers some physics people, but that's how the problem is set up. So this is feet per second when we do velocity. So when we want velocity, velocity is the rate of change of position. So we could say v of t or s prime of t, right, the derivative. And so we are going to get that function first. So that's going to be negative 32t minus 10. And we want to find the velocity at 5 seconds. So we just plug in the 5. And that is going to give us negative 170. And that's going to be feet per second because velocity is a rate. The next one says compute the acceleration. So the acceleration is the derivative of the velocity function. So we could call acceleration the second derivative of position, the first derivative of velocity, or it has its own name, which is just a of t. So the derivative of my velocity function is just going to be negative 32. And that should make sense, right? Because we know if you have taken physics, you know acceleration due to gravity is a constant. Okay, so this all kind of fits in. So if we had units there, we call that feet squared per second because we're saying the rate. The next question is something we have to use the calculator for. It says, when will the ball hit the ground? I guess we could set this equal to 0 and solve with the quadratic formula, but we're going to solve it this way. So I'm going to graph. We have a little calculator icon, and this is a faster way to do it. I can tell my y-intercept is 2,717, so I know I'm going to have to change my window pretty high for y. I don't need it very low because that's the ground, but we'll make it maybe 3,000 here. So here's the picture. I need to extend my x as well, it looks like. So maybe I do 20. Okay, and I can see this point. So I can do a second calc 0 for that. And I get that the time is 12.722 seconds. So I'm saying S of t equals 0 when t is 12.722 seconds. What will the velocity of the ball be at impact with the ground? This is a question we might want to know. How fast is it going when it hits the ground? So I'm going to do v of that value. So v of 12.722. So I could do that on my calculator since I have a decimal. Reminder that we have the x value here, so I can type the x in, and I have that number. So I have negative 32 times the x value minus 10. And I get that the velocity is negative 417.119 feet per second at that moment. So looking at the next page, we're just going to do some practice with some more second derivative problems in a couple of different contexts. We are going to skip example 3. I'm not worried about doing that one, and go down to example 4. So we have a second derivative, and as I said, second derivatives aren't any new rules, but sometimes as we take derivatives, things get more complicated in terms of what we have to use. So let's see what happens on this one. So I have second derivative of y of t, so we have to find the first derivative first. And this is derivative of cosecant is negative cosecant of t cotangent of t. So t is not the best variable to have with some of these trig functions, but now I see to take the second derivative that I have to use the product rule. So the second derivative of negative cosecant is going to be negative cosecant t cotangent of t, and I actually have to make that positive because we have this negative here already. We'll do positive in a different color just so it's not so confusing. So times the second function, which is cotangent of t, and then we're going to have a plus that's going to become a minus, right? Because of the fact that this first function is negative. So we have plus negative cosecant of t, and then times the derivative of cotangent, so that's times negative cosecant squared of t. So now we have a pretty big mess. We're just going to basically simplify from here. So this first term is positive, so I have cosecant t cotangent squared of t. I have two negative signs here, right? So those are going to cancel and become positive. So I have plus cosecant of t cosecant squared of t. So we can rewrite this piece as cosecant cubed of t. So you might see this factored as you go through this process, but that is the final answer on that one. Moving on to the last problem, this is a little bit of second derivative work with implicit differentiation. So I need to get to the second derivative, so we're going to take the first derivative first. So I get 2x plus 2y dy dx equals 0. From there, I'm going to solve for dy dx. So I'm going to subtract the 2x and divide by 2y, giving me negative x over y. So to get to my second derivative, right, I have to work from this. I don't have a lot of good information now about what y is, but we will have to work with that later. And I do see that I'm going to have to use the quotient rule. So the second derivative, so we're taking the derivative of this side. The derivative of this side is going to be negative 1 times y minus negative x times dy dx, which is the derivative of y. In my denominator, I get the denominator squared, so I'm going to have a y squared. Now, it's okay to have x and y in my derivative, but I don't want to have a dy dx. So for this dy dx, I have to plug in what I found dy dx was in the last part. So looking at this is going to give me negative y. This becomes a positive, so plus x times negative x over y, because I'm plugging in dy dx, what I found there. Simplifying wise, I'm probably going to see some sort of like getting rid of the complex fractions. So what I can do is I can multiply the top and bottom by y. I'm going to do one more step in between before that. So if I multiply the top of the fraction and the bottom of the fraction by y, so this is by 1, and I distribute, I'm going to come over here so I have room, I get negative y squared. Here this cancels, so I get minus x squared. And in my denominator, I get y cubed. So that is the second derivative of this function. So what you're going to do in your homework packet, I'm just going to give you guys one page on this, and you probably can complete it during class since I'm not here today. Looking in the packet, hopefully you can try it quickly. So you're just going to be doing page 26. So complete page 26, we'll check that as well as the homework that was due today.